Hello and welcome to Lecture 1, covering sections 1.1 to 1.6, and on the topic of physical measurements. All right, our objective in this group of sections is to identify base units in the SI system, which is the international system, understand the concept of derived units, familiarize yourself with order of magnitudes prefixes and symbols, and define the key terms below, as well as use simple dimensional analysis. All right, so let's get into our terms. This is going to be a big part of this set of lecture notes is defining the terms, and then we have a few examples to wrap it up. All right. So, first of all, we have the term a dimension. A dimension is simply a physical quantity. It is analogous to a unit and relates to something called dimensional analysis. So when I say analogous, I really mean that a unit and a dimension, those are really interchangeable terms. They're synonyms for each other. Just kind of depends on the context. Okay, the dimensions for this class are as follows. T for time. Notice dimensions are traditionally put in brackets. It doesn't come up that often, but that is the way they're distinguished from a unit, which is put in parentheses. So uppercase T for time, uppercase L for length, uppercase M for mass, uppercase phi, that is the Greek letter phi for temperature, and that's probably because T was already used for time. And then finally, uppercase N for substance amount. Okay, so those are the dimensions that would be relevant to this class. Okay, our dimensional analysis will really only involve time, length, and mass. All right, so now a unit. Okay, so more often than not, we'll be thinking about units rather than dimensions. A unit is a physical quantity. Okay, simply a different way of looking at a physical quantity as compared to a dimension. So dimensional analysis could just be called unit analysis. Again, right, stressing the similarity between those two terms. The units can be base or derived. We'll talk about both types. Okay, so let's get into the base units and the derived units. Okay, so units, base units and derived units are specific types of physical quantities. Well, what's the difference? Well, base units describe all of physics with 7 base units. Okay, and in this class, the base units are S for seconds, M for meters, kg for kilograms, uppercase K for Kelvin, and the word mole for moles. Okay? So these 5 base units cover this entire class. The only base units we're leaving out, which would be for another physics class, are the ampere and the candela. Okay? On the other hand, derived units are composed of base units. So get some examples. All right? So one example, e.g. just means example, is a Newton. Okay? It's represented by its own letter, uppercase N, but you can see it's composed of base units, kilograms, meters, divided by the squared seconds. Okay? So kilogram meters per second squared is how you might say that. Another example is the joule, represented by uppercase J. It is the kilogram meter squared per second squared. So similar to the Newton, but with an extra meter in the numerator. Okay? Those are examples of derived units. Not all expressions of units have names. So meters per second is called velocity, but there's no special name for the unit. There's not a velocitron or something. Okay? So something to keep an eye out for, the idea of when a derived unit has a name and when it doesn't. Okay? Okay? So an order of magnitude is a power of 10. Simply that. Okay? That's order of magnitude. It's kind of science jargon for a power of 10. All right, so what do I mean by that? Well, it's a term used to describe multiplying or dividing by a specific power of 10. Let's do an example. A million is 8 orders of magnitude larger than a hundredth. Okay, that's a good example. So a hundredth, like a centimeter, because that's a hundredth of a meter, is 8 orders of magnitude smaller than a million. Or the way I worded it here, a million is 8 orders of magnitude smaller than a hundredth. What would that look like? Will look like this, right? Because a million is 10 to the 6. Okay, a million is 1 followed by 6 zeros. Thus, it's 10 to the 6. A hundredth is 2 zeros behind the decimal point. So it's 10 to the negative 2. Negative exponents mean something smaller than 1. So if I want to find out how much bigger a million is than a hundredth, I divide a million by a hundredth, and I get 10 to the 8. That's the order of magnitude difference. That's why I can say a million is 8 orders of magnitude larger than a hundredth. There's particular notation for powers of 10. that can be combined with units, derived or base. For example, a mm is a millimeter. The lowercase m denotes a thousandth, or 10 to the negative 3 in scientific notation or order of magnitude notation. The way we would say that is it's a thousandth of a meter. A millimeter is a thousandth of a meter. A megajoule, uppercase m here instead of lowercase m, okay, megajoule, is 10 to the 6 joules because it is a million joules. So how do you remember the terms and the letters that correspond to orders of magnitude? Well, you have to have a table handy like this before you get used to them, okay? So, for example, the common ones are kilo for 1,000, mega for a million, giga for a billion, sometimes tera for a trillion, milli for a thousandth, very common, micro for a millionth, also very common, nano for a billionth, you're going to see that a lot more in electricity and magnetism, pico for things that are very small, all right, and so on. There's some less common ones, right? Centi is actually common, like a centimeter, but deci, deca, and hecto are less common, okay? What about significant figures? Maybe you've heard of them before, most likely. These are reliably known digits. In scientific notation, it is the number of digits after a decimal. For example, 6.62607 times 10 to the negative 34, which by the way is Planck's constant, it's a fancy constant in physics, has 6 significant figures because there are 1, 2, 3, 4, 5, 6 significant figures. Okay? All right. When performing math, both the uncertainty range and uncertainty must be considered. That is, performing math with significant figures. Here's an example, and this is one we have to pay attention to, or I advise you pay attention to this example, okay? So 6.13 plus or minus 0.2 centimeters multiplied by 4.1 plus or minus 0.1 centimeters is equal to what, okay? Well, this plus or minus business refers to error. So that means you have a measurement of 16.3 centimeters, but you're unsure about a fifth of a centimeter, 0.2 centimeters. Likewise, you have another measurement, which is 4.1 centimeters, and you're unsure about a tenth of a centimeter. So what happens when you multiply them together? Well, you get 67 plus or minus 5 centimeters. Well, where did that come from? Well, first of all, the reason there's only 2 significant figures in the final answer is because one of our measurements only had 2 significant figures. I often refer to that as the weakest link. That limits the number of significant figures that are in our final calculation. So again, when multiplying values, even though this measurement had 3 significant figures, our final answer must only have 2 because one of the measurements only had 2. But what about the error? The error only has 1 significant figure. That seems inconsistent. No, that has to do with the uncertainty range. Let me explain. So you look at the max and the min. Okay? The maximum value that the measurement could be would be 16.5 times 4.2. Well, why is that? Well, 16.5 is the biggest that the measurement could be that has an average of 16.3. See, because you add the error. Okay? Likewise, if we add the error to our 4.1 measurement, we get 4.2. If we subtract the error from both measurements, we get the minimums. So now we're going to take this difference between the max and the min. So we're taking the max product minus the min product. The product because multiplication, right? Okay, so that gives us 69.3 minus 64.4. Ah, so there's our error of our result. Okay, but I have it as 5, not 4.9. Why is that? Well, because 4.9 is accurate to the 10th, seems to be accurate, I should say, to the 10th of a centimeter. But our final result, based on our limitation of significant figures, is only accurate to the centimeter. There is no point something here, right? That means that we have to round this to the nearest centimeter. We have to, because our final result is only accurate to the nearest centimeter. Thus, our error only has 1 significant figure. Okay? So there's an interesting flow of how to calculate significant figures as well as range of error. Okay? Our last key term here is the idea of percent error. We're going to see this in quite a few of our labs. It is a way to compare observed value with expected or theoretical value. For example, an experiment measures the speed of light as 3 times 3.00 times 10 to the 5 kilometers per second. But the accepted value is 2.998 times 10 to the 5 kilometers per second from presumably a more accurate experiment. So then the percent error in this case would be the absolute value of the observed minus the theoretical divided by the theoretical times 100. So this is the formula you always use for percent error. If we plug in our numbers, then we end up with 0.07%. Not a lot of error, okay? So it turned out our result was pretty accurate. Well, depends how close we want it to be, okay? All right, so hopefully these key terms and their definitions for dimensions, variables, orders of magnitude, significant figures, and percent error have all made sense. All right, there's not really a key formula for this section, so I decided to include this. This is just the atomic mass unit, all right? And I included it because it's a good demonstration of a number that has a lot of significant figures and has an order of magnitude because it's written in scientific notation. And of course, the order of magnitude is very small because an atomic mass unit is a tiny portion of a kilogram. And before I move on, I forgot that I wanted to mention that the 0.07 shows up here because of the uncertainty range. Because our measurements were only accurate to because if we multiply this percentage by the original number, and I don't show the process here, but if I multiply this percentage by the original number, then it will only go to the third decimal place after, or the third place after the decimal. And for that reason, I wouldn't write, say, 0.071 or something. I have to limit it here because I'm limited by the uncertainty range. Very similar to the example above when we defined significant figures. All right? So do it yourself. Make sure that this result makes sense. That, in other words, that the percent error only has one significant figure as dictated by the uncertainty range. All right, so let's get on to our examples. All right, so there's two types of examples that we're going to do for practice. Type 1 are simple problems that involve conversion and order of magnitude considerations. Type 2 are simple problems that use algebra and systems of equations to solve for unknown dimensions/units. All right? So example 1 is a type 1 type of example. How many cubic meters is a penny? I give you the diameter in inches, the thickness in inches, and the conversion between inches and meters. Okay? Okay, so how do we go about doing that? Well, first of all, we're going to assume a cylinder. So we'll write down the volume equation that we'd look up for a cylinder, which is pi r squared, just the area of a circle, multiplied by t for thickness. All right, well, we're going to convert our radius to 1/2 of the diameter because we're given the diameter, and remember to square it. Okay, still multiplying by thickness. Then I'm going to put my conversion factors within the process of multiplication. So here, because I'm given my diameter in inches, but I want to convert it over to meters, I have my conversion right here. See? So I have my 0.75 inches, that's the diameter as given, multiplied by the conversion factor. Notice the units. Notice my conversion factor is correctly meters over inches, which allow me to cancel out inches. Good way to check that you're doing it correctly. All right? And what's very important is that conversion factor is within the parentheses, so I'm squaring the whole thing. And of course dividing by 2, because I want to divide the diameter by 2. And then here, I multiply by the thickness with the same conversion factor. Again, taking note that the inches cancel out. All right? So now we can just plug that into a calculator just as written. All right, making sure to include the parentheses where necessary, and we get our final result, 4.3 times 10 to the negative 7 cubic meters. You might be like, wait, that's a really small number. I mean, that means that it's less than a millionth of a cubic meter. Well, that's absolutely right, okay? Because volume is quite dramatic in that respect, right? A penny is a tiny, tiny portion of a cubic meter. A cubic meter is about 3 feet by 3 feet by 3 feet, so imagine a 3 foot by 3 foot by 3 foot tank, and how many pennies would it take to fill that tank if there was no dead space between the pennies? Maybe you're melting them down or something. Well, in that case, it would take, according to this, well, think about how many it would be, right? If it's less than a millionth, it's about half a millionth. That means it would take about 2 million. You could also just raise this number to the power of -1, and that will give you about 2 million, which is how many pennies it would take to fill a cubic meter. Okay? All right, let's look at the second example, which is the same type of problem, just a little bit more complex. Gold can be compressed to a thickness of 1.04 micron. Now, a micron is a 10 to the -6. That's a millionth. Micron is just a term that comes up a lot. It's heavily used as an expression for a millionth. In terms of, and it means a millionth of a meter. Another way you could write it based off the table on the previous page would be mu m. Mu is a Greek letter, and that would represent a micrometer. By the way, mu for a millionth is the only time a Greek letter comes up as an order of magnitude notation, interestingly enough. Okay, so we're making gold leaf. Gold has a density of 19.32 grams per cubic centimeter. We can see here that density is just mass per volume, if you're kind of not familiar with the definition. So density, represented by the Greek letter rho, which just looks a lot like a P, is just m for mass over v for volume. Notice here that this expression isn't in terms of the units, it's in terms of variables. M here doesn't represent meters, it represents mass. It's a variable, a common one, that represents mass. And that's a good thing that you want to make sure that you're checking at first when you start this class. Because although it might seem obvious that you're not going to mix up meters and kilograms, you might because you see an M. So ask yourself, is it a variable or is it a unit? And here, V is for volume, right? Which has units of cubic meters. And M has units of kilograms, okay? Rho, the variable, has units of kilograms per cubic meters, okay? What mass of gold is needed to cover a statue with gold leaf with a total surface area of 12 square meters? So how do we go about doing this? Well, let me show you my workflow. First, we want to find the total volume of gold leaf. Well, total volume is simply area times thickness, because in this case, our covering is actually a rectangle. If we were to kind of unfold all the gold leaf covering, it would just be a very thin rectangle, right? A rectangular solid, I should say, right? So area, we know, is going to be 12 square meter, and we know the thickness is 1.04 microns. All right, that checks out. So that gives us a total volume of 1.2 times 10 to the negative 5 cubic meters. So bigger than a penny, right? Okay, in fact, about 2 orders of magnitude bigger. Now we want to convert that density that we were given into kilograms per cubic meter. Why would we want to do that? Well, because our volume is in terms of cubic meters, and our final answer we want to give in terms of kilograms. I don't specify, you could give me grams, but I want to convert the density to kilograms per cubic meter so that we can then solve the problem in a way that makes sense. Okay, so to convert the density, rho, given to us in terms of grams per cubic centimeter, we need to do a conversion, and a two-step conversion, unlike the single-step conversion in the problem above. First, we need to convert grams to kilograms. Well, every kilogram is 1,000th of a gram. All right, or I should say every kilogram is 1,000 grams, which means every gram is 1,000th of a kilogram. So this is the necessary conversion. You know it's correct because we have here, this is how many if we to speak this, if we were to write this expression in words, this would be kilograms per grams. Well, there's 1,000th of a kilogram per every gram. And then notice that that checks because the grams cancel. Likewise, if we want to convert cubic centimeters to meters, we remember that we want to, first of all, convert centimeters to meters. So, well, there's 100 centimeters per meter. That allows the centimeter to cancel out. But that would just cancel a single centimeter. So then we have to remember to cube our conversion. But the important thing is we're not just cubing the conversion like this. We have to remember to cube the entire conversion. So in other words, that's telling us that 100 cubed is going to give us how many cubic centimeters there are per cubic meters. Because think about this exponent. I'm going to distribute this exponent onto both the cubic centimeters and cubic meters, as well as distribute the exponent onto the 100. Well, what is 100 cubed? Take a second. You know what 100 cubed is? Type it in a calculator if you need to. It's 1,000,000. So that's telling us that every cubic meter is 1,000,000 cubic centimeters. In other words, if we go back and think about that tank that's 1 meter by 1 meter by 1 meter, it would take 1,000,000 little cubes that are 1 centimeter by 1 centimeter to fill it. But of course it would, because you would stack 100 in a line, and then you stack 100 of those 100 lines. Well, that's 10,000. So now you have a layer that's 10,000 cubes thick, and then you're going to stack 100 of those 10,000 thick layers. That's 1,000,000. All right, so now we have our density of gold in terms of kilograms per cubic meters. All right, so here I didn't put the units in here, but here I correctly finally included them. Sorry for leaving them out in that step. And it, of course, is a much bigger number. It's 19,320 kilograms per cubic meter. But that makes sense because there are a lot more cubic centimeters per cubic meter than there are grams per kilogram. All right? Another way to write it in terms of scientific notation is 1.932 times 10 to the 4 kilograms per cubic meter. Okay? And you can confirm this by looking it up to make sure that you did the conversion correctly. All right? So our final step, since we were asked for mass, is simply to multiply rho times v. Why do I know that gives me mass? Because of the equation that was given in the words of the problem. All I've done here is just cross multiply both sides by v, which just tells me m equals rho v. Plug in the numbers because everything is in the correct units now. Cubic meters cancel. I get my final answer with the units of kilograms. Always a good thing to make sure your final answer is giving you the units that you expect and want. Put in the calculator, and I find out that I'm going to need 0.241 kilograms. In other words, 241 grams in order to cover the entire statue. All right, so those are my two examples of type 1 problems that involve conversions and order of magnitude considerations. And here are some more for further practice that you can solve and post the solutions if you want. All right, well, let's do a couple of examples that involve dimensional analysis. All right, so let's take a look at example 5. Suppose A equals B to the N times C to the M, right? So this is just a mathematical expression. A is some physical quantity, and it has dimensions of LT, length times time. Meanwhile, B has dimensions of length squared over time. Why do I know it's over time? Because t to the negative 1 is the same as dividing by t. Remember, negative exponents are the same as dividing by that variable to that exponent. Okay? So in other words, L times t to the negative 1 is the same as L squared over t. All right? Lastly, C has dimensions of L times t squared. Okay? Then the exponents n and m have what values? We need to find n and m in order to satisfy this expression. It's very mathy, isn't it? Okay? But it's all with, units that really, or dimensions that really exist. All right, so we write out the expression just so we can change it. So this expression here is going to become this. Why? I've just substituted in the expressions for A, B, and C respectively. That's it. And just made sure to have the n and m because, of course, B and C are raised to a particular power, an unknown power that we're going to solve for. A is just raised to the power 1, which we don't have to write, so it remains unchanged. Now, this expression here, this single equation, a exponential equation, can become a system of equations based on the laws of exponents. Right? I'm sure this is something you did in a pre-calc class and likely forgot. All right, so how do we do that? Well, we simply match up the expression for L and the expression for T. So we have to make sure that all the L's agree in terms of their exponents and all the T's agree in terms of their exponents. Well, on the left-hand side, we just have an L to a 1, so that's where I have 1 equals. On the right-hand side, I have an L squared times n and an L times m. And remember, the laws of exponents tell us that when we multiply by exponents, it becomes addition. And when we take an exponent to another exponent, it becomes multiplication. So our 2 raised to the power of n becomes 2n, and our 1 raised to the power of m just becomes m. Meanwhile, our 2n multiplied by m becomes 2n plus m. We do the same thing for t, checking the exponents on all sides of the equation, and we get another straightforward algebraic expression. So now we just simply solve this for n and m. I think it's easier to do a substitution. So I'm going to write m in terms of n, and then we're going to substitute in m in terms of n into the bottom equation. So all I'm doing here is just replacing m with 1 minus 2n, which I got from the upper equation. In other words, this is the L equation, this is the T equation. All right, and now we have an expression with only one unknown, n. We simply solve for it. You see my simplification process there, and we get that n is 1/5. Okay, now that I have n is 1/5, I can easily back substitute into this expression and find m. All right, so that's all I'm doing here, is just replacing n with 1/5, and that gives me that m is 3/5. And I highly recommend, check it. Plug it back in to the original expression, this one here, and make sure it works. All right, so let's do it one more time. The period of a simple pendulum is the time it takes to make a complete oscillation, otherwise known as a swing, assuming that the potential physical variables that can affect the period are gravity with dimensions of L over t squared, because it turns out gravity is an acceleration. We'll talk about why acceleration has those dimensions later. The units would be meters per second squared. The pendulum arm length with dimensions of L, units would be meters, and the mass of the bob, dimension m, units would be kilograms. The initial angular deflection, dimensionless, right? represented by theta. It's an angle, either measured in radians or degrees. It wouldn't matter. It's dimensionless in both cases. Using dimensional analysis, what does this tell us about the period as a function of these properties? Okay, so we're going to write an equation, right? I'm saying that the period is potentially a function of g, L, m, and theta. Okay, this is just a function, kind of functional form like you'd seen in math class. We don't write everything in terms of functions. Lots of the times it would be clunky and unnecessary, but here I'm simply calling attention to it. All right, T stands for period, okay, not time, not the dimension time, right? But it's a variable that I'm using because it is the traditional variable used for period. Usually we use lowercase t for some elapsed time, and we use uppercase t for some repeating time, like that of a swinging pendulum. G, on the other hand, is the variable that's used for gravity traditionally. Okay, L for length and m for mass probably already makes sense. Okay, and again, theta for an angle. So now we're going to take that expression and write it as an exponential equation, just like in the example above. Okay, we know that period is raised to the first power. We know that gravity has dimensions of L over t squared. I'm telling you that. You don't need to know that ahead of time. That's stipulated in the problem. Okay, but we'll certainly learn why. We know that length has dimensions of length. Duh. And we know that mass has dimensions of mass. And we're trying to solve for A, B, and C. Just like above, we were trying to solve for N and M. So very similar problem, just one step more difficult because now we have 3 unknowns. Okay, so now note that theta is not included. Well, that's the whole thing. Dimensional analysis has a big limitation. It can only address things that have dimensions. And if there's something dimensionless, like an angle, it simply will not come up. We don't know anything about it. So it's one of the big limitations of dimensional analysis. Okay, but we can do something pretty neat here. So we're going to go ahead and turn this into 3 equations, again, just based off the laws of exponents and making sure that we match up each side of this main equation with the yellow highlighting. Okay, so first our t equation just becomes 1 equals negative 2a, and again, that's using the same logic as example 5 above, right? As make sure that, all right, well t, okay, so I have a t over here in my gravity term, and t, well, it's t to the 2, but it's in the denominator, so that's the same as t to the negative 2. And if I'm raising negative 2 to the a power, that's just negative 2a. Oh, okay. And there's no t's over here, so that's my whole t equation. Do the same thing for L. Now, on the left-hand side of the equation, there's just a t. So that means that, well, L doesn't show up. And in fact, for that matter, neither does M. All right. So, yeah, there was 3 unknowns, but the equations become really simple, don't they? Right? We don't have to even do any substitution. We can just solve for each one at a time. A is negative 1/2, right? I guess we do a little substitution here because we are but we just straight up solve for A, substitute it into our second equation, our length equation from the exponential equation, and that gives us that B is positive 1/2, right? That's the exponent, of course, and well, C is 0, okay? So there's no C. Oh, that's interesting. All right, so then we're going to take the exponents and plug it back now into not the dimension equation, but the variable equation. Notice, right, this equation of all the brackets was for the dimension. It's interesting that, of course, t is the variable and the dimension, but the brackets hopefully distinguish between the two. So here we have the variable representing period, the variable representing gravity, the variable representing length, and the variable representing mass. Okay, and all with our solved for exponents. Well, look what it simplifies to. It simplifies to the fact that period is just the square root of L over G. That's because 1/2 is the same as the square root. An exponential of 1/2 is another way of writing a square root. Okay? And the negative 1/2 puts the G in the denominator of that root. Okay, neat. Well, technically, it's actually t equals some function of theta times the square root of LG. Because, I'll show this here, because, remember, we don't know anything about theta, limitation of dimensional analysis. But do note this. The dimensional analysis told us something really interesting, really fascinating, that t, the period of a swinging pendulum, is independent of its mass. And I really like that because we're going to see that weeks from now in the chapter on oscillations. And that actually is an amazing fact about pendulums. Of course, it only works if there's no air resistance, but that is actually absolutely true, that the period of the pendulum in a vacuum is independent of its mass. And we could come to that guess based on dimensional analysis. In fact, more than a guess, a very solid hypothesis. Okay? All right, so hopefully that example made sense, as well as the other dimensional analysis example and the previous ones using conversions in order of magnitude. I got a couple more that you can solve on your own for further practice if you want, and post the solutions. So thank you so much for listening to Lecture 1 covering sections 1.1 to 1.6, and stay tuned for a few further lecture videos. Bye.